This video is on simple harmonic motion. Question 1. Define oscillation. Oscillation means back and forth motion. Question 2. Give 3 examples of oscillations. An airplane wing vibrating up and down. The branch of a tree vibrating back and forth. And a pendulum on a grandfather clock. So remember, when an object oscillates, it starts from one end, it speeds up, has a maximum speed in the middle, slows down and stops on the other end, at the other end. Then it goes and it speeds up, has the maximum speed in the middle, and then it stops at the other end. And then finally, that's one oscillation, or one cycle. Question 3, define periodic. It means repetitive. Question 4, define period. What are the units? The period is the time it takes for an oscillating object to complete one oscillation or revolution. Period is given in seconds. Question 5, define amplitude. Units. The amplitude of an oscillating object is its maximum distance from the equilibrium position. Amplitude is given in meters. Question 6, define frequency. Units. The frequency of an oscillating object is the number of cycles or revolutions the object makes per second. Frequency is given in cycles per second or revolutions per second or 1 over seconds or hertz. Because cycle is not a real unit and revolution is also not a real unit. That's why the units of frequency is 1 over second or hertz. Question 7. What is a mathematical relationship between the frequency and period of a wave? F is equal to 1 over t. Question 8. State the equation for the angular frequency for an object undergoing simple harmonic motion. So omega is equal to d theta over dt. Write this down. Theta is angular position. Omega is angular speed. So in one revolution, in one circle, it's going to be 2 pi radians over the period. And solve for the period. We can clearly see that angular frequency omega has units of 1 over seconds. Because omega has units here of radians over second. Radian is not a real unit. Okay, here's a review. Number 9. The slope of the displacement versus time graph tells us the velocity of an object, and the slope of a velocity versus time graph tells us the acceleration of an object. Question 10, review. Define equilibrium. Equilibrium is when sigma f equals 0, a equals 0, v equals constant. Because remember the equation sigma f equals ma. So if sigma f on the left-hand side is 0, then a on the right-hand side is 0, and if a is 0, v is constant. Question 11. Give the name, define, and give the units of each variable from Hooke's law, F equals minus k delta x. So F is a force from the spring on the mass, has units of newtons. K is a spring constant, has units of newtons over meters. If K is large, then the spring is strong and stiff. If K is small, then the spring is weak, easy to stretch, easy to compress. Delta x, it's the displacement from equilibrium position, has units of meters. So the minus sign here is called the restoring force, has no units. The spring's restoring force always tries to return the mass to its equilibrium position. So take a look at this image here. If you start a spring at x equals 0, it's not moving. If you stretch it to x equals plus a, and you release it, x here is positive. If you look at this equation, if delta x is positive, and there's a negative sign, then f is negative. That means the force points towards the equilibrium position. Now imagine if you release this object and the object goes all the way to the left. Now it's at x equals minus a, minus amplitude. So if it's x equals minus a, delta x is delta x is negative. We got a negative sign here. Two negatives make a positive, so f is positive. So that means if the object is at x equals minus a, the force is pushing it to the right. So if you're anywhere on the right-hand side, x is positive, delta x is positive. We have a negative sign here, so force is negative, because negative times a positive is a negative. If this mass is oscillating left and right, anytime you're to the left of x equals 0, delta x is negative. Here's a negative sign. Two negatives make a positive. That means the force is positive if you're anywhere to the left of x equals 0. Question 12. A mass lying on a smooth horizontal surface is attached to a spring and is stretched from its equilibrium position. It is then released. Label the forces on the mass. So you have an object here, you release it. What forces do you have? Force normal up equals force gravity down, force of spring on the to the left. And it's on a smooth horizontal surface, so there's no force of friction. Question 13. Use a pencil and ruler, draw and label an acceleration versus displacement graph for simple harmonic motion. So F equals ma equals minus k delta x. Solve for a. So on the left-hand side you have a, on the right-hand side you have minus k over m. K over m is a constant, it doesn't change, times delta x. So the slope depends on the value of k over m. So remember that delta f external and a must always point in the same direction. But v and a and also v and f external don't have to point in the same direction. So to draw an acceleration versus displacement graph, we're going to use this equation. A equals minus a constant times delta x. Which looks like this. Question 14. Derive the defining equation of simple harmonic motion. So F equals ma equals minus kx. Second line, we divide both sides by m. We let omega squared equals k over m, which is a constant. So a equals minus omega squared x. That's it. A on the left-hand side has units of meters over second squared. On the right-hand side, you have meters for x, so omega squared must be 1 over second squared. Question 15. What are the main characteristics of simple harmonic motion? Okay, so frequency is independent of amplitude. Imagine what that means. It doesn't matter how far you stretch it. Once you let it go, the time it takes to complete one cycle is going to be the same if you stretch it further or less further. Number 2, displacement velocity and acceleration versus time graphs follows a sine or cosine pattern. We'll see more of that later, hopefully. And finally, amplitude and period are constant. That means there's going to be no force of friction, which brings the amplitude to 0. It's just no force of friction. Question 16. Derive the equation for the time period of a mass spring system. So, if you have a mass spring system, let's look here. F equals ma equals minus kx. We know that a acceleration is a function of time. We know x displacement is a function of time. We could also write this down. mx double prime equals minus kx. The two dots on the top means two derivatives. because two derivatives of displacement give us acceleration. So we have this equation. Let's take a guess about x as a function of t. Is there a function, x as a function of t, where if you take two derivatives of it, we get a negative sign, and then we could put it here, and then the left-hand side equals the right-hand side? So let's take a guess. Let's let x equal x sub 0 sine omega t plus phi. X sub 0 is called the displacement or the amplitude here. This is the amplitude. If we take two derivatives, we get this answer. So put this on the left-hand side and put this original equation on the right-hand side of this equation and see if the left-hand side equals the right-hand side. So plug those equations into this differential equation. And the left-hand side equals the right-hand side. Except omega squared equals k over m. So we'll just say omega squared equals k over m. And omega is 2 pi over t. Angular speed is 2 pi radians per period. Solve for period. We could put this in the denominator here. To get this function here. Question 17. State the equation for the time period of a simple pendulum. That's the equation. T equals 2 pi root L over G. So that's the time it takes for a pendulum to go from one side to the other side and back to the other side, its original side. And we use a small angle approximation. So this is only for theta less than 10 degrees. Question 18, draw two waves which are in phase. So the crests line up with the crests, the troughs line up with the troughs, and the amplitude of the two waves don't have to be equal. So this is an example. The functions y equals 5 sine of x and y equals 12 sine of x are in phase. So look at this image here. On the right-hand side, the crests line up with the crests, we're good. In the middle, the troughs line up with the troughs, we're good. And on the left side, the crest of the red curve does not match up vertically with the crest of the black curve. So those are not in phase. Question 19, use a pencil and ruler, draw two waves which are out of phase by 180 degrees. So crests line up with troughs. The amplitude of the two waves don't have to be equal. So this is an example. The functions y equals 8 sine x and y equals minus 15 sine x are out of phase by 180 degrees. Because the crest of one, if you draw a vertical line, is going to match up with the trough of the other one. Question 20. Draw two waves which are out of phase by 90 degrees. So example, the functions y equals sine x and y equals cosine of x are out of phase by 90 degrees. So remember this, displacement and velocity are out of phase by 90 degrees. Velocity and acceleration are out of phase by 90 degrees. Displacement and acceleration are out of phase by 180 degrees. Question 21. The total energy of a simple harmonic oscillator is given by the equation E total equals E kinetic plus E potential equals 1/2 mv squared plus 1/2 k delta x squared equals a constant. In the figure below, label the locations of all of this. So you have this image. You have an object starting from the equilibrium position, it's not moving. You stretch it to x equals plus a and you release it. This object oscillates between plus A and minus A forever. Label the location of E kinetic max. We're at maximum kinetic energy at the middle, because once you release it from x equals plus A, it speeds up. After the middle, it slows down and stops. Then it speeds up to the right. Once it hits the middle, it's going to be at maximum speed. Then it's going to slow down and stop, go back to x equals plus A. So kinetic energy max is at the equilibrium position. Where is kinetic energy equal to 0? Well, that's on the right end and the left end. Where is the potential energy max? Potential energy is 1/2 k delta x squared. So potential energy is maximum when delta x is maximum. So that's at x equals plus A and x equals minus A. Where's potential energy minimum? Look at this equation, 1/2 k delta x squared. Potential energy is minimum when delta x is 0. So x is 0. So when is the acceleration of this object maximum? Well, remember this graph, excuse me. F equals ma equals minus k delta x. So acceleration is maximum at x equals plus A and x equals minus A. Acceleration is max at x equals plus A and x equals minus A. Where is acceleration minimum? Where is acceleration equal to 0? In the middle. Remember, you start at x equals plus A, it speeds up, and then after it crosses x equals 0, it slows down and stops at x equals minus A. So acceleration is 0 at x, at f equals ma equals minus k delta x. So delta x is 0, where A is minimum. Where is velocity max? Velocity is maximum in the middle. And velocity is minimum, or 0, at the ends. X equals plus A and x equals minus A. Question 22. What is the mathematical relationship between the energy and amplitude of an object in simple harmonic motion? Energy is proportional to amplitude squared. Question 23. Use a pencil and ruler. On the graph below, draw an energy versus displacement graph for a mass on a spring with 3 curves. Okay. Potential energy versus displacement, kinetic energy versus displacement, and total energy versus displacement. So, remember, we're looking at this equation here. Looking at this red line, horizontal, that's total energy. That's kinetic energy plus GPE. Look at this happy face. Where is the energy maximum at the ends and 0 in the middle? That's F equals ma equals minus k delta x, which is potential energy. So the happy face, the pink curve, is potential energy. And what's the blue? What kind of energy is 0 at the ends and maximum in the middle? That's kinetic energy, because kinetic energy is 1/2 mv squared. So the V is maximum in the middle. Question 24. On the graph below, draw an energy versus displacement. Draw an energy versus time graph during one oscillation for a mass on a spring with 3 curves. Potential energy versus displacement, kinetic energy versus displacement, and total energy versus displacement. So Energy is conserved, so at every location, kinetic energy plus potential energy equals the total energy. So that's why the black total energy is a horizontal line. So let's assume that we release the object from rest at the right. If we release the object from rest at the right, then kinetic energy is going to be the blue line because the object starts at 0 speed and 0 kinetic energy. If we release the object from the very right, in the very beginning, potential energy, which is 1/2 k delta x squared, is going to be positive because you're releasing it at x equals a being the amplitude or the displacement. So black line total energy, red line potential energy, blue line kinetic energy. Question 25. A mass attached to a string is stretched to the right of its equilibrium position, released and undergoes simple harmonic motion. Draw a velocity versus time graph of its motion. So look at 1. 1 is like x comma 5 comma 0. Okay? It's on the horizontal axis. That's where position 1 is. Then once you release it, the x decreases and the velocity increases, so then you go to 2. And then after it passes the equilibrium position, at point 2, it's going to continue to go to the left. The velocity decreases, and x also decreases, goes more negative, once we hit 3. Now what's happening at 3? That's where at x equals minus a. We have maximum displacement. Then the object starts moving to the right and it speeds up. Question 26. A pendulum makes 22 oscillations in 42 seconds. Determine the period and frequency of the pendulum. So that's how you do it. Question 27. A 600-gram mass is hung at the end of a vertical spring. The spring stretches 22.5 centimeters. Determine the spring constant. So the spring was not stretched until you put a mass on it. It's a vertical spring. So this is the equation here. K delta x points up, mg points down. And then just solve for k. Part B, how much further will it stretch if a 900-gram mass is hung from it? So we already know K. So we just added 900 grams to the 600 grams. Question 28. A 497-gram mass is attached to a spring with a spring constant of K equals 9.87 newtons per meter and oscillates horizontally on a frictionless surface. The mass is displaced 6.54 centimeters from its equilibrium position and released. Part A, determine the maximum speed of the mass. So, in the very beginning, we have only potential energy. At the very end, we have it looks like we have both here. Potential energy plus kinetic energy. So let's solve for V. We know x sub 0 is 6.54 centimeters. And we know x final is going to be 0 meters Because at 0 meters, that's when the object has a maximum speed. And just solve for v. Part B, determine the speed of the mass when it is 3 centimeters from its equilibrium position. So we'll use the same equation. We'll start with this. Then we'll end up getting this. Part C, determine the acceleration of the mass when it's 3 centimeters from its equilibrium position. So F equals ma equals k delta x. Solve for A. Question 29. A 40-gram mass undergoes simple harmonic motion at the end of a spring. Its maximum displacement from equilibrium is 18 centimeters and period is 1.2 seconds. So part A, determine the frequency. We have this equation. Part B, determine the spring constant. We have this equation. Part C, determine the maximum speed. So we have law of conservation of energy. In the beginning, we only have potential energy, the left-hand side. And at the end, we only have kinetic energy. So when we solve for V here, x is equal to 0. Part D, determine the maximum acceleration. F equals ma equals k delta x. The maximum acceleration is at the end, when delta x is maximum. Part E, determine the speed of the mass when its displacement is 8 centimeters. Once again, use the law of conservation of energy. Part F, determine the acceleration of the mass when its displacement is 8 centimeters. So F equals ma equals k delta x. Question 36 vertical springs, each with a spring constant of 2570 newtons over meters, are individually hung on a wall. Each spring hangs a 35.5 kilogram mass. Determine the period of the mass when it oscillates. So it has 6 springs. When they're hung individually, you just multiply all the number of springs. Question 31. On planet X, an IB student wants to determine the acceleration of gravity near its surface by using a pendulum. The time it completes 20 oscillations is 35 seconds on a 0.825 meter long massless ring. Determine the acceleration of gravity on planet X. So we get about 10.6 meters over second squared. Please check out what I did. Question 32. A 34.5 gram mass is attached to a horizontal spring. The mass performs simple harmonic motion according to this equation, 0.975 cosine 12t. Part A, determine the amplitude. It's just the value in the front. Part B, determine the frequency. So remember, omega equals 2 pi f. Multiply both sides by t. No. We were given this earlier. 12t equals 2 pi ft. Here. This equal to 2 pi ft will tell you the frequency. That's exactly what was happening. That's good that this solution is not a function of time, because if it was, that means as time changes, frequency changes. Part C, determine the position of the mass at 0.682 seconds. Make sure your calculator is in radians, not degrees. So we have a solution. Part D, determine the spring constant. So K is equal to 4 pi squared F squared M. And we just plug in all the numbers. Just solve for K from this problem here. Question 33. The position versus time graph of a pendulum is given below. Part A, what is the period of this pendulum? It's here, right? Time to complete one cycle is 5 seconds. Part B, what is the maximum displacement of this pendulum from the equilibrium position? So we take a look at this graph and we see the maximum displacement is about 0.13 meters. Part C, what is the angular velocity of this pendulum? Omega is equal to 2 pi radians over period, 2 pi radians over 5 seconds. 5 seconds is the time to complete one oscillation. Part D, write the equation which describes the position of this pendulum as a function of time. So, this is the general equation, right? This object did not shift up or down, this graph. So D here is equal to 0. It didn't shift left or right either if we let sine be the function. So this is our function. 0.13 is the amplitude or the maximum displacement. And as you know, B is equal to 2 pi over 5. Part E, what would be the position of this pendulum 4.5 seconds after it's released? Just put everything in the equation from part D. Part F, what would be the position of this pendulum 11.5 seconds after it's released? Just put it in. Part G, what would be the maximum speed of this pendulum? So the maximum speed, we need to find the slope at maximum. How do we find the slope? 2 points. Found 2 points, I took the slope of those 2 points. So this graph has a unit of here x versus t. To take the slope, it's like we're finding v versus t. Part H, write the equation predicting the velocity of this pendulum as a function of time. So we have an equation for displacement as a function of time. So just take the derivative to find a function of the velocity. Part I, what will be the velocity of this pendulum 4.5 seconds after it has been released? What I highlighted for part H, use that function for part I. And for part J, ditto, use that equation from part H. Part K, what would be the maximum acceleration of this pendulum? So let acceleration take the derivative of the velocity or the second derivative of the displacement to get an acceleration graph, acceleration versus time function. Now we know that the limits of sine are between -1 and 1. So the acceleration is this. That's the magnitude. 0.205 meters over second squared. Part L, what would be the acceleration of this pendulum 4.5 seconds after it has been released? So we have an equation from part K, just plug it in. Part M, what is the length of this pendulum? So let's use this equation. Solve for L. Part N, based on the graph, at which times is the velocity of this pendulum 0? The velocity is 0 by looking at the graph. It's when the slope is 0. So the velocity is 0 at the very top, the very bottom, very top, very bottom, very top. That's N. O, Based on the graph, at which times is the acceleration of this pendulum 0? Remember, the acceleration is 0 when the object is in the very middle. So that's at 0, 2.5, 5, 7.5, 10. Question 34. The position versus time graph of a pendulum is given below. So this is very similar to the last problem. Part A, what is a period? So the time it takes to go back to its original position is 10. So how long does it take to go from 0.9 to 0.9? It's 10. I apologize. It's going to go to 0.68. How long does it take to go from 0.68 back to 0.68? 10 seconds. What is the maximum displacement of this pendulum from the equilibrium position? Okay, the answer is 0.65. So it's like 0.64, 0.65. Yeah. 0.65. I said 0.68. That's my fault. Part C, what is the angular velocity of this pendulum? It's 2 pi over t. Part D, write down the equation which describes the position of this pendulum. So this looks like cosine, yeah? Because we're starting at a maximum. So let's use this equation. A cosine bt plus c plus d. The displacement is 0.650. B is omega. We already found omega. T plus. Now, this was not shifted left or right, so C is equal to 0. And this was not shifted up or down, so D is equal to 0. Part E, what would be the position? Part F, what would be the position? So for E and F, just use this equation that's highlighted from part D. Okay. So G is asking for the maximum speed. The maximum speed, we need to find the slope, where the slope is maximum. So we need 2 points once we draw that line, that tangent line. And then we'll take the slope using those 2 points. Part H, write the equation predicting the velocity of this pendulum as a function of time. So we solved for x. Now take the derivative of x to find v. I and j is asking for the velocity at a certain time. We're just going to use the equation we got from h. Part K, what will be the maximum acceleration of this pendulum? Take the derivative of v, or the second derivative of a, and we get this equation. We know the limits of cosine are between +1 and -1. So let's just assume this cosine here, let's just say it's -1. Negative times a negative is a positive, so we're only looking at this. So the maximum acceleration is 0.257 meters over second squared. Part L, what will be the acceleration of this pendulum? 18.5 seconds after it's been released. So L and M want us to use this equation for acceleration that we got from K. And when is the velocity 0 based on the graph? Well, the velocity is 0 is when the slope is 0. The slope is 0 at 0, 10, 0, 5, 10, 15, 20, 25, 30 seconds. And O says, based on the graph, at which times is the acceleration of the pendulum 0? The acceleration is 0 when you're in the middle. And in the middle, you have maximum speed. So the acceleration is 0 at 2.4, 7.6, 12.4. You get the point. The horizontal axis, when you cross the horizontal axis. Yeah. So there's an approximate sign here because it's not exact.